Hello and welcome to another video on tolerance stackup analysis. In this video, we'll be exploring how to do a tolerance stackup analysis for welded sheet metal parts as shown. So this is basically a part of a larger assembly, and these two brackets in pink color are welded to the green color tubes, and these two tubes are welded to a pipe as shown by the weld lines. So the pipe is inserted into the holes on the rectangular tubes and it is being welded over here all around, and the two brackets are being welded onto the green rectangular pipes using these welds. So these are the weld lines shown over here and one on the other side. Similarly, one over here, one on the other side. And this pink color bracket has a hole as shown, which is used for mounting. And the stack up which we are doing over here is to find out the maximum span between the mounting points. So here is one mounting axis, here is another mounting axis on the other side. It's a symmetrical design. What is the maximum possible span which we can have, considering that we are taking into factor the part tolerances of the individual parts and also the tolerances due to welding and assembly tolerances of the overall weld assembly. So let's see how we can do that. So the first step is to create the loop diagram. So that's the first logical step. So we are basically trying to find out the maximum span between the mounting points. Hence we are finding this specification from this axis to this axis, which is A to B. That specification we need to find. For that we can start from here. So the first variation is from the axis of the bracket to the edge of the bracket, which is variation number 1, which is forming part variation. So this part is developed using sheet metal forming, and the variations which are coming of the center axis based on the edge of the bracket will be covered in specification number 1. Then specification number 2 is about weld distortion. So when a bracket is welded onto another member, there is weld deviation or weld distortion which takes place, which contributes to the overall assembly tolerance. So the second source of deviation is weld distortion. Third is width variation of the pipe. So when the pipe is manufactured, it will have inherent width variation, that is nothing but the part variations of the rectangular pipe. And then there will be assembly tolerance when the two rectangular tubes are welded to the pipe, the circular pipe, which is shown over here. So the positional deviation of the assembly and the weld distortion will basically be factored into this specification number 4. So this is the assembly tolerance of the tubes to the pipe, the tubes being the rectangular tubes. And then specification number 5 is again the width variation of the pipe, which is similar to specification number 3. Specification number 6 is also weld distortion, which is same as specification number 2. And specification number 7 is forming part variation, which is again similar to specification number 1. So this is the loop diagram. We start from A and end at B, and we are calculating the specification for this span between the two axes. So here is the data from the part drawings. So this is the part drawing of the bracket, of this pink color bracket, and the important dimension over here is this dimension, which locates the axis of the hole with respect to the edge surface of the bracket. So here this specification is corresponding to specification number 1, which is the part variation, which is 15.8 plus or minus 0.25. So plus or minus 0.25 is due to the inherent manufacturing process, which is sheet metal manufacturing process, and also whatever the additional post processing takes place, that will yield a tolerance, a part tolerance of 15.8 plus or minus 0.25 in the location of this hole with respect to this edge. We are only using coordinate tolerancing and dimensioning technique. There is no GD&T over here. So that is specification number 1 and also specification number 7, which is this. So both are the same, 15.8 plus or minus 0.25. Now specification number 2 and specification number 6 is the weld distortion contribution. We can consider that as plus or minus 0.25. Of course it varies depending on the type of welding, the type of material being used, the type of part which is being welded, it will vary a lot. For this example, we'll consider this to be plus or minus 0.25 mm. Of course, it can go higher for larger weld areas, plus or minus 0.5 also it can go. We're considering here over here a conservative plus or minus 0.25. Now, the next variation, the source of variation is the width variation of the pipe, which is specification number 3, which is this one, this dimension over here. So this is an assembly drawing of the two tubes which are welded to the pipe, and this is 40 plus or minus 0.25, and this is specification number 3. Similarly, specification number 5 is the same because both the tubes are the same, and specification number 4 is the welded assembly tolerance, that is the positional, basically how the tubes are positioned with respect to each other, and also the weld distortion accounted along with it. So that specification is 140 plus or minus 1. So number 4 is 140 plus or minus 1. Again, number 5 is width variation of the pipe, which is same 40 plus or minus 0.25, and specification number 6 is weld distortion, which is there is no dimension associated with it, only the tolerance. And again, specification number 7 is only the part variation, so 15.8 plus or minus 0.25. So these are all the dimensions: 15.8, 40, 140, 40 and 15.8. We add them all up, we get 251.6, and we add all of the tolerances up, we get plus or minus 2.5 mm. So the specification for this A to B gap is 251.6 plus or minus 2.5 mm, and we can calculate the maximum span by adding this 2.5 mm to this, which is 251.6 plus 2.5, which is 254.1 mm. So in the worst case, the maximum span which can occur between A to B for these two mounting brackets will be 254.1 mm. This is the absolute worst case scenario, considering the weld distortion to be plus or minus 0.25 and the assembly tolerances and part tolerances as shown. So this is just a very simple example for welded assembly. So we can see that we have to take into factor the weld distortion, especially when two sheet metal parts are being welded, or even non-sheet metal parts. When two parts are being welded, we need to consider the weld distortion as a factor which gets added up into the tolerance stack-up. One useful standard is the ISO 13920 standard, which gives general weld tolerances which can be used for tolerance stack-up purposes.